Let me get this out of the way right now. The thumbnail says prehistoric sharks, but I need to come clean to your face. There isn't a single true shark in this entire video, not one. Hear me out. The creatures we're about to meet, with spiral buzzsaw jaws, scissor-toothed upper and lower dentitions, and an ironing board sticking out of their backs, are officially not sharks. They belong to a group called ratfish. Yes, ratfish. We've got catfish, batfish, flatfish, and now ratfish. Sounds like I made that up for a bit, right? But that's actually the common name for this whole lineage. I didn't invent a single word. So you think you clicked on this video for a prehistoric shark showdown, but actually, you're watching a full-blown case of identity theft. Fish that look like sharks, but are really just cousins of sharks. So what are they, really? And why do they look so much like sharks? That's what we're going to peel apart layer by layer today. This lineage is so sick, and so absurdly old, way older than you probably think. Every time I talk about any animal, the first thing I do is place it on the tree of life. If you don't know which branch it's sitting on, everything else you hear about how weird it is just floats in empty space. All three of today's stars, along with true sharks, skates, and rays, belong to the same big class. Chondrichthyes, the cartilaginous fish. The name gives it away. Their skeletons aren't made of bone, but cartilage. The same stuff you feel when you pinch your nose or wiggle your ear. Their entire body frame is soft. This class splits into two major subclasses. One is elasmobranchi. Sharks, skates, rays, and sawfish all live here. A good tell. They have 5 to 7 gill slits on each side of their body. The other is holocephali. That's the chimeras, which, yes, is the group commonly called ratfish, plus all their extinct relatives. And today's stars all sit on that second branch. But I need to draw an honest line here, or I'd be misleading you. The extinct species we're about to cover are not technically chimeras themselves. They're close relatives of chimeras. They're cousins to ratfish, not ratfish proper. I call them ratfish for simplicity, and because they share the same branch. But scientifically, they're in the extended family. This kind of nuance matters, and honestly, knowing it only makes them cooler. So half the suspense is gone. They're the ratfish side of cartilaginous fish, not true sharks. Now let's see just how old this branch really is. Here's the second gut punch. The common ancestor that sharks, ratfish, and all these cousins share was alive over 400 million years ago. 400 million, with an M. Here's your scale reference. This lineage is older than trees, as far as we know of. Actual trees on land showed up just a little bit after that 400 million year mark. Let that sink in. When this group of cartilaginous fish was already diversifying in the oceans, there wasn't a single proper tree on Earth. Picture that, the forest you walk through. That old tree outside your window. They're all latecomers. Meanwhile, the ancestors of these fish were already there, long before. So where exactly do today's three sit on the timeline? Dial it back. The Carboniferous, over 300 million years ago. The Permian, between 250 and 290 million years ago. We'll get to precise dates for each one soon. But first, lay down that deep time framework. You're not just looking at ancient animals. You're looking at a few of the most ridiculous offshoots on a lineage older than trees. First up, Helicoprion. Chinese common name often translates to spiral tooth shark. It was named and described by Karpinski in 1899, and the name literally means whorl tooth. It lived during the Permian, roughly 290 to 250 million years ago. When it was first dug up, scientists had exactly one thing: a spiral coil of teeth, like a circular saw blade rolled up, nothing else. Here I need to explain the core mechanism that runs through this entire episode, or nothing that follows will make sense. Cartilage doesn't fossilize easily. Chondrichthyans have cartilaginous skeletons, and in the vast majority of cases that cartilage doesn't survive deep geologic time. It decomposes, it gets lost. So what this whole group leaves us is basically just teeth. Teeth are hard enough to stick around, That's why their reconstructions have historically been like opening a blind box, because scientists really did have nothing but a pile of teeth to work with. And that's how the history of wild hypotheses begins. My favorite part: you have one spiral of teeth. Where on the animal do you put it? Some said it curled up from the upper jaw and looped toward the nose. Others said it sat on its back, used for display or intimidation. The on-the-back guess wasn't pulled out of thin air. It had a logical basis. Chondrichthyans are covered in placoid scales, small structures with an enamel-like covering over a dentine core, essentially the same material as teeth. They're more resistant to decay than cartilage. So if some placoid scale got modified and enlarged, it might also preserve relatively well. So the idea that this spiral might be some enlarged structure on the back was a reasonable possibility at the time. Then, the evidence started to narrow. In 1950, Danish paleontologist Svend Erik Bendix Almgren found a crucial specimen in Idaho, catalog number IMNH 37899. This one actually preserved cartilage along with the teeth. With that reference frame, he confirmed the tooth whorl was in the mouth, not on the back, not on the nose, in the mouth. Then came the real game changer. In 2013, scientists CT scanned that specimen and discovered that the spiral actually sat inside the lower jaw, not spilling out like some early reconstructions had shown. See what happened there? Uncertainty tightened, step by step, from a wild guess about location, to confirmation in the mouth, to the exact position inside the lower jaw. So what did it use it for? That's still open. Based on current evidence, maybe it sliced through shelled prey. Maybe it slashed soft-bodied animals. And let me clear up a common internet myth. It did not spin like an actual buzzsaw. The rotation only refers to the way new teeth kept growing, and the spiral gradually enlarged over its lifetime. It wasn't a power tool. Size estimates range from 10 to 14 feet, with some pushing it to 24 feet. Why so much variation? You guessed it. Cartilage doesn't preserve, so we mostly have to extrapolate from that single tooth whorl. As far as we know, that's Helicoprion. One spiral jaw not weird enough for you? Next up, we're giving you a double dose. Asterisk Edestus. Asterisk, you can call it the scissor-tooth ratfish. It lived during the Carboniferous, roughly 313 to 307 million years ago, a bit earlier than Helicoprion. Interestingly, its debut story is almost identical, found in the 19th century as isolated, bizarre skeletal fragments and initially placed everywhere in the mouth, on the back, even on the tail. These two are often referenced together in the same scientific papers, a kind of echo of that earlier wild hypothesis era. But Edestus has one killer difference. While Helicoprion had one crazy tooth whorl, Edestus had two. Upper jaw and lower jaw, both protruding outward, coming together like a pair of open scissors. In 1900, paleontologist Sir Arthur Smith Woodward described the concept of a giant shark, armed in both jaws with multiple rows of teeth, as sufficiently startling. Translation: that's a big WTF. So how did those scissors work? This is a textbook case of hypotheses follow technology. For about a century, the leading idea was that they closed like scissors. Snip, snip. Then in 2015, some evidence pointed to a different motion, a vertical slash, like chopping downward with a knife. Then in 2018, scientists analyzed CT scans and found two joints that suggested a more specific feeding sequence. Edestus might have used its tooth whorls to slice prey, then used the lower whorl to pull the prey back into its mouth. Cut, then retrieve. Notice what happened here. It's not that earlier scientists were dumb, it's that the tools got better. CT gave us the joints, which gave us a new interpretation. This is what I always say. Treat uncertainty as the edge of the map, not as an embarrassment. And that edge keeps getting pushed outward with new tools. Size-wise, conservative estimates based on tooth whorl length put Edestus at over 20 feet. Conservative, as far as we know. The first two were big. You're probably expecting the third to be even bigger and more menacing. But actually, the third one is a tiny little guy. Stethacanthus, about 2.5 feet long, lived roughly 360 to 280 million years ago. It didn't make its name through size, it made it through the thing on its back, an ironing board-shaped dorsal fin. Scientists call it the spine brush complex. Brush refers to the layer of placoid scales, that same tooth-like material we talked about, covering the top of that ironing board fin, and also a patch on its head. Picture this, a platform on your back, topped with tiny bristles, and a matching patch on your noggin, like a tiny toupee. So what was it for? Honestly, the scientific community is not sure. And the uncertainty here is significant. There are two main hypotheses, and I'll be straight with you about the evidence strength. I won't oversell them. First, mate attraction. The basis is that only males seem to have had this structure. That sounds plausible, right? But here's the nuance. Many papers actually only say that only males have been found. Those are not the same statement. Only males have it is a functional conclusion. Only males were found is just a sampling reality. To make it messier, some references mention another species, *Simorium*, that shares similarities with *Stethacanthus*, hinting that Simorium might actually be the female of Stethacanthus rather than a separate species, but that was never firmly established. So the mating hypothesis is on soft ground. Second, predator deterrence. In 1984, paleontologist Rainer Zangerl studied the microscopic anatomy of the spine brush complex and suggested it might have been inflatable. I could only read the abstract of that paper. He also floated a really cool possibility. The brush on the back, combined with the patch on the head, might have visually mimicked the open mouth of a much larger fish when seen from certain angles. So a tiny critter could Photoshop itself into a giant, gaping maw to scare off anything that wanted a bite. This is the core model I love most. Cute and terrifying are often two faces of the same survival pressure. An ironing board dorsal fin could have been a mating billboard, a fake giant mouth, or both. The bottom line, still inconclusive as far as we know. I'm not going to declare a winner because the evidence isn't there yet. We've talked about a bunch of extinct monsters. Now let's pull the lens back to the present day, because here's something many people don't realize. This 400-million-year-old lineage never actually disappeared. Its living descendants are still swimming in the oceans right now. Spotted ratfish, deep-sea ghost sharks, rabbitfish, these are all living holocephalians, all connected to sharks through that same common ancestor over 400 million years ago. They're the modern-day version of ratfish. So when you say prehistoric sharks, this lineage has actually been continuous. It just changed its face. Most of them live in the deep sea. That's worth pointing out, and it ties naturally into our evidentiary boundary. Because they live in deep, dark places, our knowledge of them is still limited. The deep ocean is one of the least understood regions on the planet. I'm not going to spin this into a panic about conservation. That's not my style. I'll just make a neutral statement. This ancient lineage has living members. They live deep, and we don't know enough about them yet. If I were to give you specific population or conservation data, I'd need to pull material. I'm not going to fabricate it. The key takeaway here is a cognitive upgrade. Prehistoric never really ended. The old and the new are just 2 points on the same evolutionary map. Let's do an honest inventory. What do we know, and what don't we know? That's the rule of this channel. Known. These are holocephalians on the ratfish side of Chondrichthyus, not true sharks. This lineage is over 400 million years old, older than trees. Helicoprion, tooth whorl, sat inside the lower jaw. Confirmed by CT scans in 2013. Edestus likely used a slash and retrieve feeding method, suggested by the 2 joints found in 2018. Unknown or still hypothetical. What Helicoprion actually cut, shells or soft bodies, remains uncertain. What Stethacanthus ironing board fin was for mating, defense, or both has no consensus, and the size estimates for these animals, those how many feet numbers, swing wildly. Why do so many answers stop at hypothesis? It all goes back to that premise we started with. Cartilage doesn't fossilize easily. That fundamental limitation means that often we only have teeth and no body. Without a body, many questions have to stay at as far as we know. It's not that scientists aren't trying, it's the boundary drawn by the fossil record itself. So that's what we currently know about prehistoric sharks, a group of cartilaginous fish that are actually ratfish cousins, older than trees, sporting buzzsaw spirals and scissor teeth. But keep your eye on that word, currently. The next fossil dug up, the next CT scan could rewrite a conclusion from today's episode. The map of this lineage is still being drawn at its edges. So I want to hear from you. Drop a comment. What other prehistoric animals do you know that look like they shouldn't even exist? Or out of today's three, asterisk, Helicoprion, asterisk, asterisk, Edestus, asterisk, asterisk, Stethacanthus, asterisk. Which one still has you scratching your head? Throw it up here and we'll dig into it together. Stay curious. There's a whole lot more out there for us to learn. And as far as we know, the most ridiculous ones might not even have been unearthed yet.